So let's suppose that somebody comes up to you on the street, as happens to me all the time as a mathematician, and hands you a rational tangle, right? If I want to do any cool mathematics with that rational tangle, I at least want to know what word in the rational tangle group spells out the tangle that I was just handed, right? So if somebody hands me the rational tangle we're seeing on the screen right here, how would we determine the TR word for this tangle? This particular tangle is arranged in a really nice way. We can kind of tell that whoever it was that made this tangle, the last things that they did, so the last two steps that they took in making this tangle, are that they did two twists over here on the right-hand side, right? So the very last things that were done were a pair of positively oriented, which there's only one orientation for twists and rational tangles, and it happens to be northwest over southeast is what we agreed on, right? And so the very last two steps in this rational tangle are a pair of twists. So t squared is going to come last because we read our rational tangle words from left to right. Right? So t squared is going to come at the end. Okay? And then you might imagine kind of erasing those twists. Let's see if I can do that right here on the Jamboard. Oh. I need a better tool here. All right, well, let's imagine that I can kind of erase those twists. And then we imagine undoing the rotation, which got us to this stage right here. When we do the rotation normally, we do the rotation clockwise. Wait a minute, clockwise, because I'm looking through a camera. Clockwise is this way. Normally our rotation goes this way. And so if we want to undo, we kind of want to figure out how is this tangle created. We just want to turn it counterclockwise. If I turn this tangle counterclockwise, I should be able to do that with Jamboard, but I think I might need to zoom out a little bit to make that happen. Now we have the twists are over on the right side of my diagram again. And I have a total of 3 of them. 1, 2, 3. Reading from, well, it doesn't matter which way I read. If I read them from right to left, then I'll have 3 of them. And then in between there was my rotation that got me from there to there. Okay. And then if I forget about those twists and I rotate one more time counterclockwise to undo the rotation that was used to create this, then I'll find out that I have these twists in the beginning, of which there are 4 in a row. So if you'll forgive my sort of bad mouse-driven handwriting, we can find a TR word for this tangle to be t to the 4th r, t to the 3rd r, t squared. Right? So that's a TR word for the tangle that we began with here. Okay, so now the idea, right, is if I want to determine the continued fraction which represents this rational tangle, and when I simplify that continued fraction, I get the rational number in lowest terms, which determines this tangle, and is determined by it. The recipe is that we start from an empty tangle, just like we start when we're making a tangle in the first place. And the first thing I would do is a series of 4 twists. Well, when I translate that into rational numbers, that means starting with the number 0 and applying this add 1 function 4 times. So it takes me from 0 up to 4. I have a nifty little scratch calculator that we can use today if we want to simplify the arithmetic bits of it. So starting from the tangle number of 0, the first thing I would do is do 4 successive twists. And every time I twist, my tangle number is going up by 1. Right? So after 4 successive twists, I now have a tangle that has a tangle number of 4. So then what's supposed to happen next? I'm supposed to do a rotation. And every time I do a rotation, I'm taking the opposite reciprocal of my tangle number. So I hit the R, and my tangle number goes from 4 to negative 1/4, right? Opposite reciprocal of 4. And then we just keep going, right? Do 3 more twists, so add 1 3 more times, then do R, opposite reciprocal, then do 2 more twists, add 1 2 more times, and then we're done. And so what develops in that process is I'd like for you to write in your group if you can, and you might have to write this on Jamboard because it's kind of a mess to typeset, but write out a continued fraction. So an expression that looks kind of like this: an integer plus the reciprocal of some integer plus the reciprocal of some other integer plus the reciprocal of some other integer, blah, 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 and so on, right? To write out the fraction that would result from translating this tangle into a continued fraction, and then simplify that fraction into its lowest terms. Right? So that's the first step that I want us to just get the practice in our groups working on that bit together. So again, the key correspondence here, right, is that when we're building a word using the functions t and r, little t and little r, right, where little t is the add one function, little r is the opposite reciprocal function. If I have a word built out of capital T's and capital R's in the rational tangle group, then those functions composed together are supposed to represent that rational tangle, and we can evaluate those functions at a single rational number, namely x equals 0, in order to do so. So what that means is that a recipe for determining a continued fraction for a rational tangle word like this one up here, t to the fourth r, t to the third r, t squared, would be to start from an empty tangle which has a tangle number of 0, and then do t 4 times, right? And each time we do t, we're adding 1 to our tangle number. So when I do it 4 times, my tangle number goes up to 4. Right? And then after that, the next step in my word is supposed to be a rotation. Right? And every time I do a rotation, I'm taking an opposite reciprocal. So 4 turns into negative 1/4. And then I'm supposed to do 3 more twists, and so I add 3 to my tangle number, and now it goes up to 2 3/4, or 11/4. The opposite reciprocal of which would be minus 4 over 11, which is kind of a nasty number, right? And then I just have to add 2 more. And I get up to this tangle number, which looks like 1.63 repeating. That's 1, if you like, in, you can convert repeating decimals into a fraction representation for a rational number. 0.63 repeating is 7 over 11. And so 1 and 7/11ths would be 18 over 11, if I'm doing that arithmetic right. And so, the claim here is that the number 18 over 11 should represent this rational tangle. Right? That is the rational number which we're going to use to stand in for this tangle. And so what I'm asking you to do when I'm asking for the continued fraction representation of this tangle is to just kind of slow that process down and show how the number 0, which is the representation of my empty tangle, right? 0 is what I started with. That in this process, what did we do? We started with 0. We added 4 to my 0, right? So I'm going to make that my first set of steps here. And then I think I'll probably just forget that 0 was there in the first place. So we'll just sort of say 4 is my first step, and it's there because that was my first set of twists that we did here. And then we did a reciprocal. And so the net result of that reciprocal, a rotation. And the result of that rotation was an opposite reciprocal, minus 1 over 4, like that, right? Then we did 3 more twists. And so the result of those 3 more twists was that I added 3 to this negative 1/4. So notice how I'm not simplifying in any of these steps. Because I'm not simplifying, we're going to get to see this continued fraction kind of unroll itself and reveal itself to us here. And then the next step would have been rotation, which again, rotation does an opposite reciprocal to that whole thing. Make that 1 look a little bit more like a 1. And then my last step was 2 more twists to finish, which is adding 2. So when I say the continued fraction representation for Q3, this is what I mean. Right? 2 plus negative 1 over 3 plus negative 1 over 4. Right? And so what we can observe right away is that once we know how these continued fractions are built, all we need to know in order to build one of them is what are the integers that are appearing in these denominators, right? They're 4, 3, and 2, but they're appearing in kind of the reverse order as when we read them from left to right in a rational tangle word, which again is not that surprising because that's how our functions were composing with one another, right? The first thing we're doing is 4 twists, and so that's kind of the innermost function evaluation that we do. It's nested inside the most parentheses by the time we've built the whole expression. And so what people will do notationally when they're working with continued fractions is that they'll write this just as kind of a vector with these 3 integers in it, 4, 3, 2. So that we know if somebody gives me 4, 3, 2, that I do this process to them, right? This process of opposite reciprocals and additions that give me my tangle number at the end, the continued fraction representation. And you'll also notice that 4, 3, and 2 were exactly the exponents on how many twists that we had in the original rational tangle word representation of our tangle. And when we simplify this all out, we get a single rational number, 18 over 11. So the point of the first exercise that I want us to do today, I guess it's the second now that you've already done one exercise, is to figure out then how could we use this number, 18 over 11, to actually untangle this tangle. Right? How can we get back to 0 starting from 18 over 11? Because that same sequence of additions of 1 and opposite reciprocals, which get me back to 0 from the number 18 over 11, are also going to give me a sequence of t's and r's, which would take me back to the empty tangle in the rational tangle group. It's the same as the set of dance steps in the rational tangle dance that we would tell the dancers to do to magically untangle the tangle that they created. Right? So if the tangle that they created when they did the dance was 4 twists rotation, 3 twists rotation, 2 twists, okay, then we as the master of ceremonies for the rational tangle dance would be able to tell them, here is the next set of dance steps you should do so that when we rip the envelope off the tangle, it's untangled. Okay? That concludes the magic trick. So I think what I want to do is recommend that you use this nifty tangle calculator that I shared out with you, this thing that I built in Scratch, and just try it. See if you can come up with almost a recipe for how could we turn this tangle number, starting from, so build the tangle like I did here first so that we have 1.63 repeating, and see if you can figure out how we could return this back to the number 0 just by using t's and r's. And keep in mind that t inverse, this thing, is actually not real for us. At this point, we can't use it because in the rational tangle dance, we only have the one twist that goes northeast over southeast, and then we have the rotation. So we can't actually use the t inverse button. That's for a different kind of activity than we're doing right now. So let's go back into groups, and I want you to figure out if you can find a set of steps in t's and r's that can get this tangle number back to 0. So what we're building towards is we're trying to build toward a strategy for how do we get back to 0 using this add 1 and opposite reciprocal operation, right? So starting from 18 over 11, we want to be thinking about how are we going to try to make that fraction simpler, right? One of the things you might notice as you start to work with these is what's happening with your denominators as you make the choices of t's and r's, because we ultimately want to try to get our denominators to start shrinking. If we can get the denominators down to 1, in other words, if we can get ourselves back to integers, then as long as we're at negative integers, we can just add t's until we get back to 0. So that's kind of the end game of this. If we can somehow shrink the denominators consistently, such that we can eventually get the denominators to be 1 and my fraction to be negative, then I know that I can get right directly to 0. So what are some of the strategies that you've hit upon, or at least some ideas that you've had in your group so far? If the goal is to try and get the denominators to shrink as much as possible, and also to get us a negative fraction, probably the first thing I want to do here is not start twisting, which is just going to start increasing the denominator more and more and more. But instead, maybe I want to start with a rotation, an opposite reciprocal, so that now the denominator that I landed in the negative rational number line is an 18, right? Which is bigger than it was at. But what's going to happen if I add a twist into this now? Negative 11 over 18, since that's between negative 1 and 0, right? If I add a single twist into it, I'm going to get a fraction 7 over 18, which the denominator is still 18, but the numerator now, 7. If I apply the opposite reciprocal to that, I'm going to get a negative rational number whose denominator is smaller. Now, my denominator's gone down to 7ths instead of 18ths, right? And so then, now it's probably time to start twisting again. And we'll stop twisting once we've gotten a positive number. And then hopefully that positive number has a numerator that is going to be, once we opposite reciprocal it, smaller than 7. Rinse, repeat, right? See if you can use that process back in your breakout groups to figure out how to get back to 0 from where we're at here. So at this point, you're sort of feeling your way through the process of making a conjecture of whether or not, given any p over q, so you hand me a rational number. Can I always find some sequence of applications of this t function and this r function? Again, it's the add 1 function and it's the opposite reciprocal function that gets me back to 0. And so you've been working on some strategies for that in your groups. So the strategy that you came up with, right, is that in order to get from a rational number p over q, let's suppose without loss of generality that it's positive, right? If I want to get that to 0, the first thing that I might do is take its opposite reciprocal to make it negative, right? And once it's negative, I'm going to add 1s, I'm going to twist until it becomes positive again, just until it becomes positive again, right? And no further. I don't want to make it too positive, just positive enough, right? Just one step past that 0 that we're trying to shoot at. Overshoot just a little bit. And then repeat the process. Take the opposite reciprocal again. You're going to get a negative fraction that we hope has a smaller denominator than before, and that we hope is an opportunity for you to work on a proof there, right? But if the denominator is smaller each time, then again, keep adding, keep twisting until we're just past 0, then take opposite reciprocal again, then keep twisting until we're past 0. Keep going, keep going, keep going. And your claim is that eventually the denominator that we get when we take this reciprocal is going to end up being a 1, and then I have a negative integer, which when I add twist again, I land right on 0 that last time. And so that feels to me like an opportunity to again, come up with a proof that this is always going to work. Let's see if it avails us for our 18 over 11 that we've been working on here. So 18 over 11 is positive. And anytime I have a positive, I want to make it negative. Apply that opposite reciprocal. And now that it's negative, I want to start moving it back towards 0 again by adding twists. And in this case, it just takes one twist to overshoot 0, right, and get me to 7 over 18. And now that I'm positive, I want to opposite reciprocal again to make myself negative, negative 18 over 7. Now I start twisting again to get me towards 0. My denominator has shrunk to 7, so this is seemingly good news. So one twist, a second twist, a third twist is what it takes me this time to get me back close to, on the opposite side of 0, on the positive side, right? Now that I'm positive again, I'll take a reciprocal. My denominator is now 3, which is, again, seems like really good news. So that when I start twisting once, twice, 3 times, I overshoot 0 just a little bit, right? I end up at 2/3. Opposite reciprocal again. Twist once, twist again, positive 1/2. Take a reciprocal. We've got a negative integer, which is great. It's exactly what we wanted. That means that we're just 2 twists away from the empty tangle. So all in all, right, we started out with this. Let me make sure I have it right there. There we go. So there's my original tangle. 4 powers of t, followed by rotation, followed by 3 powers of t, followed by rotation, followed by 2 powers of t. And then this remaining word over here, RTR, 3 t's, and then an R, 3 t's, and then an R, 2 t's, and R, and then 2 t's, would then be the inverse that we would get for this. If I were going to try to do this just by using the inverses of the generators themselves, remember the inverse of R was itself, because R has order 2 in the rational tangle group, and the inverse of the twist was a combination of 5 rotations and twists, RT, RT, R. Right? So if I wanted to do this the hard way, which I guess is the simple way, but it ends up being a lot longer of a word, right? The first thing I would do here is undo one of these twists with an RT, RT, R, undo the next one of these twists with another RT, RT, R, and then undo that rotation, now that I've undone those 2 twists with a rotation. Then I would have to undo 3 twists with an RT, RT, R 3 times. RT, RT, R, RT, RT, R. And then undo a rotation again, and then undo 4 twists at the end. R, RT, RT, R, RT, RT, R, RT, RT, R. And so we would have to conclude that the inverse of this tangle can also be expressed using this sort of nightmarishly long string of R's and T's. So one of the sort of sales pitches of using the rational tangle fraction invariant to do this is it gives us a process where instead of having to think about the algebra of my generators and what their individual inverses is, I can instead think about rational numbers, and that sort of, it black boxes all the same algebra inside of it, when we think of r and t as just being the opposite reciprocal and the add 1 operations. And so this way of finding an inverse is a lot more efficient than this nasty long way of trying to find the inverse. And particularly if you're going to ask a bunch of participants with ropes in their hands to actually dance this out, probably we want them dancing this version rather than that version, just because, you know, we'd be there all night. So the last bit today is figuring out how to do the translation from a fraction into a tangle. So you all did it with technology, right? You sort of guessed your way around until you figured out, how do I make a tangle that has a fraction of -5/8. But I wanted to recommend a way that we can do that that is more systematic. So we could sort of figure out why the steps that you ultimately discovered do in fact work. Because what we're really doing is asking, if you give me a rational number, how can I write out a continued fraction of the form that we've been talking about today, that has, an integer minus the reciprocal of an integer minus the reciprocal of an integer, and so forth? How do I write a continued fraction that gives me this rational number? So here's the process I would recommend. We take the number, we round it up to the nearest the next greater integer. So starting from -5/8, the next nearest integer we would round up to is 0. So I'll round -5/8 up to 0. And so then I just need to figure out 0 minus the reciprocal of what is going to give me -5/8. Well, starting from 0, I have to subtract 5/8 to get there. So I want this 1 over something to equal 5/8. So in the denominator, I want the reciprocal of 5/8. That's 8/5. So there's my first step. Right? And then the next step, I'm going to take that 8/5 that I just wrote down and round it up also to the next largest integer. Well, when I round up 8/5 to the next largest integer then is 2. So I'll get 2. And then the question is, 2 minus what is going to give me 8/5? Well, since 2 is 10/5, I know I'm going to need 2/5 when I subtract it from 2 to give me 8/5. But I want a reciprocal here, so I'll turn my 2/5 into 1 over 5/2. 1 over 5/2, and I'll put everything else back in place here. So it's 0 minus 1 over all of that. Right. And now I have this 5/2 that's right above my head here, and I'll do the same thing. I'll round it up to the next largest integer that I can find. Round up. 5/2 rounds up to 3, I believe. If I'm doing that right. And 3 happens to be 1/2 larger than 5/2. And then I need to turn that 1/2 into a reciprocal. That's 1 over 2. And now that 2 is an integer, and so I know that I can be done. So when I back my way up into everything, I'll have 2 minus that. Oh boy. I'm going to run into my other fractions here. Let me nudge this down a little. Okay, and then it's 0 minus that. And so now that I have a continued fraction representation of the rational number, -5/8, what that is supposed to allow me to do is then to pick out, I'm going to write this in bracket notation that we used from before. For bracket notation, we're going to start in the innermost denominator and work our way up. So I'll start from my 2 down here and read 2, 3, 2, 0. Right, would be a bracket notation for that continued fraction. And therefore, that gives me a recipe for how to write Q2 as a product of the T and R generators for my rational tangle group. These numbers, these entries, are just telling me how many of my twists I'm doing in between all of my rotations. So everywhere I see a comma, that's going to be one of my rotations. So I'll have these 3 R's that are sitting in there. And then the number of twists are 2 followed by 3 followed by 2. I believe this is what folks got for this one. So t squared r, t cubed r, t squared r gets you to -5/8. Right? And so that should give you a dictionary to go from rational numbers to rational tangles. We figured out the rational tangles to rational numbers dictionary. We just tell you all have to work on proving that your strategy always works. But that this lets us go back and forth between the two worlds perfectly, right? Each different rational tangle has a different rational number associated with it, and vice versa. If you give me a rational number, I can supply for you a rational tangle that has that as its fraction. So I could build this rational tangle now using, a couple of ropes and a square frame or whatever. And so being able to negotiate both of those different viewpoints is what gives this complete invariance its power, right? Instead of doing difficult questions about rational tangles, like how do I find their inverse using the T and R generators of the algebra, I instead translate it over into rational numbers, and I can find the inverses in much nicer ways using rational numbers instead. So just to wrap up, for the rational tangle that I gave you in the assignment, now that it's been revised to fix a typo, you find out, I saw both of your groups had already started doing this. You find out that the tangle that I have you build has a tangle number of just -1. So despite the fact that it has 3 twists followed by a rotation, followed by a twist, followed by a rotation, followed by 2 twists, a rotation, and another twist, even though it has all these different maneuvers that are required to make this tangle, it turns out that the tangle that we end up with is quite simple. It's just -1. And so knowing that tangle number gives us the quickest way possible to find the inverse of this tangle. To find the inverse of the tangle, I just need to return that fraction to 0. And I can do that with a single step in this example, just by adding 1. Just by applying one more twist, in other words. Right? So there would have been no good way of knowing that this long, complicated tangle word was really only one twist away from being trivial. But having the tangle number, being equipped with knowing its tangle number is -1, guarantees that for us. So trading that hard tangle algebra for simple rational number algebra is a really, really good trade to make. And hopefully by the end of class today, now we know how to travel between those two worlds, to trade a question about rational numbers for a question about rational tangles, or vice versa.